In this example problem, we're going to discuss how high water will spurt out of a water bottle when you're on an airplane. So this happened to me a few months ago. I was carrying a rigid plastic water bottle, filled up at the airport, and sealed it. And then sometime after the plane took off and got up to some altitude, decided to get a drink of water, and I was surprised that the water spurted out of the bottle. So this is a hypothetical problem. I'm going to make some assumptions and simplifications here. This is not going to be an exact calculation, but set this problem up. Suppose we have a rigid water bottle and we do not fill it to the top. There's some airspace above the water, and then we seal it, screw on the top and close the drinking port so it's a sealed system. This particular bottle has a straw that goes towards the bottom, and then a tilted drinking port you can open and close. Let's suppose that the cabin pressure became 0.98 times 10 to the fifth pascals, where at sea level, atmospheric pressure 1.013 times 10 to the fifth pascals. So the passenger opens the drinking port, the water spurts out. And first, conceptually, why does the water spurt out of the bottle? Well, let's go ahead and a crude drawing of the bottle system here. But on the left, we've filled it 80% full of water. My attempt at drawing a straw that goes towards the bottom of the bottle, and tilted over at the top is the seal, the drinking port. In flight, we open the drinking seal up, and so the short extension of the straw is now vertical, and the water spouts up, drops fly every place. And why does that occur? Well, I'd have you note that we sealed the water bottle at atmospheric pressure 1.013 times 10 to the fifth pascals. That's pressure 1 inside the water bottle. Pressure 2 is 0.98 times 10 to the fifth pascals. It's a smaller number. So pressure 1 is greater than pressure 2. The pressure in the bottle is greater than the atmospheric pressure at the open end of the straw that's above the top of the water bottle. So lower pressure here for P2. Pressure is represented by force divided by area. Well, let's take the straw and the drinking port to be the same area. And we have a situation then, because pressure 1 is greater, force 1 is going to be greater. The force inside this straw on some blob of water, let's say right here at the water level, force 1 upward is going to be greater than the force 2 that's going downward. Force 2 being the force that derives from the pressure number 2 inside the cabin of the airplane. So we have more force going upward than we have downward, and we get a spurting stream of water here. I'm not bringing in the force of gravity, just considering what's happening in the force balance because of the pressure in the system. We have more pressure on the inside of the bottle than we have on the outside of the bottle. So we do get an upward stream. Let's go ahead and calculate the approximate height of the stream of water. Well, I'm really using a simplified version of Bernoulli's equation when I do this analysis. And this is really more of a static situation where the velocity is 0 for the situation of the fluid at point 1 and at point 2. We have pressure 2, we have pressure 1 inside the chamber here. Let's take that to be off to the side here at this water level in the bottle. It'd be pressure 1 at this point, and pressure 2 in the open drinking port. And well, you could kind of consider, let's do a long drinking port with a straw that goes upward here, and just worry about the static situation, kind of like a barometer. How high a column of water can be supported by this greater pressure inside the water bottle compared to the lower pressure of the cabin air. Well, cutting out the kind of kinetic energy related term in the Bernoulli's equation, 1/2 rho v squared, and taking H equals 0 here at pressure 1, or doing that point, and H2 would be this height of the column in this long straw. Then this height is the result of this pressure difference, pressure 1 being greater than pressure 2. Rho here is the density of water, g is the acceleration due to gravity. So I am doing more of a static pressure balance situation. I'll comment at the end on the approximations that I'm making here, what might be wrong. But let's put in the numbers. So at sea level, we seal the water bottle. That's pressure 1 inside the water bottle. In the cabin of the plane, after it's at some altitude and the cabin pressure decreases a little bit, I'm just picking a number here, 0.98 times 10 to the 5th pascals. It's actually lower when you get up to full altitude. And then density of water, 1,000 kilograms per cubic meter, acceleration due to gravity, and H. You should pause and do this calculation on your own calculator, and see if we agree at the end. Let's go ahead and pull up a little bit here. So subtracting the pressures, we get 3.3 times 10 to the 3rd for the number that's on the left. Multiplying 9.8 and the 1 times 10 to the 3, I get a 9.8 times 10 to the 3. Divide both sides, and you don't have to put in the powers of 10. They cancel. The 10 to the 3rds cancel on both sides. So it's 3.3 divided by 9.8. So I came up with 0.337. This is in meters. We're in standard metric units for this whole calculation. So I get 0.337 meters, 33.7 centimeters. Converting this to inches for the United States population of students, more familiar with that in common practice. So 13 inches roughly would be the height of the water above the water level that's in the bottle. So this is an approximation. Bernoulli's equation, we can't have any friction with the water going up the straw, and that's not going to be true here. There's going to be turbulence, there's going to be friction, so this calculation is not totally valid. Also, we don't have a pressurized, maintained, pressure 1, the atmospheric pressure is not maintained. As the water exits the bottle and goes up, this volume inside the bottle, where the air is going to expand and the pressure is going to drop. So we don't have a constant atmospheric pressure, 1.013 times 10 to the 5th pascals, as the water rises in this straw. So as I say, this is an approximate number, 13 inches, 12 inches, 10 inches, ballpark. And if you do this experiment on your own in a plane and carry this type of bottle, don't wait too long after takeoff to do the experiment. If you wait till you're at full cruising altitude, you'll get quite a spray of water coming out the top of the bottle, and you might spray the person in front of you. So we don't want that to occur. Be safe as you do physics experiments. If you'd like to see some more of these sample physics problems and also astronomy, you could go to these websites, free, no registration. The videos are listed, short description, how many minutes long they are, and the astronomy site also has some general interest astronomy videos, not just related to an introductory astronomy course. Ask your instructor if you have questions, and keep practicing.